Hello, everybody, and welcome back from spring break. I hope you had a relaxing time, if not, a fun time. Maybe you had a little bit of fun while you were out, but I hope you enjoyed your spring break and got to, at least visit, play online some. Not necessarily visit in person, of course. We should still be social distancing, but hope you got to visit and meet with some of your friends a little bit. I have discovered that I really miss the opportunity of telling stories and interacting in a normal way, and I just coming back, I just tons of stories in my head that I want to tell, and so I'm going to share this one with you real quick, just for entertainment purposes, and just because I like to tell stories. But before I tell the story, it is time for a hidden talent. My hidden talent is sewing. When I was young, being raised by my single parent mother, if something ripped, tore, or I got a patch or something that needed to be sewn onto something, she basically taught me how to sew once and said, "Okay, boy, if you need it, sew it." And so from the time I was little, I could sew. When I got a little bit older, I was still sewing by hand. My wife, one Christmas, got me a sewing machine, and I can sew with it. As a matter of fact, let me reach over here. Ugh. This is the first quilt I ever made. It's kind of a small quilt for like a child's bed, but this is my first quilt. It's comfortable. It's pretty neat, but there's the proof. Well, on with the story. I used to think that I had common sense, and I have determined that I do not, because the COVID crisis, everybody started out, no, you don't need to wear face masks. Now it's like, oh yes, you should wear face masks when you're in public. Well, you can't buy face masks, so I can sew. I'll make a face mask. Downloaded the instructions, following them step by step. I got to step number 5, which I thought was going to fold up into a nice, neat little face mask, but it was put the straps on, and this is what I had. Gabe came by and said, "Dad, how is this going to turn?" I thought it was going to wrinkle up or something, and get kind of small, but what it was I had read the instructions, and I had made the face mask using inches, and the instructions were in centimeters. So I ended up making a Hagrid quality, or a Hagrid size, a Hagrid size face mask. There you go, Beaker. There. Since then, I have again, get rid of that. I have made a few others. I made Misty a nice, this is the same pattern that's supposed to be, that's Misty a nice little face mask. And then I started making those the 3-dimensional ones, it has a little, and I made a couple of those. This one has a felt liner in it. So anyway, we've made several now. And sorry, Beaker. Here we go. Good deal. Enjoy today's lesson. Thank you. Okay, everybody, we are starting a new chapter this week. It's chapter 6. It's about work and energy. The main topics in the chapter are work and energy, conservation of energy, and power. In the interest of time, we're going to spend this week on work and energy. We won't actually talk about conservation of energy as an independent topic. I may throw in a comment or two in one of the videos, but we won't do that as a standalone thing. And then next week we're going to talk about power. So let's talk just a little bit about work. Work is probably one of the easiest concepts in physics, because work is simply force times distance. This formula right here. That is really the key to work. Is just remember, it's force times distance, which makes the only thing that I'll trick you with, or the only thing that will mess you up, is if an object does not move, no work is done. Take a look here at this. Again, classic example. We got a guy here. He's applying a force. The force causes the box to move in this direction, and therefore work is being done. Again, remember the formula: work equals force times distance. The unit for work is the joule, named after James Prescott Joule. And for those of you that are just wondering, hey, whoop, there he is with a bunch of red marks all over him, but that's James Prescott Joule right there. Now take a look at this example here. So if I'm pulling with my force, we're taking a look at the guy here on the left. If I'm pulling in this direction, which is up his arm, I'm pulling up this way. but the object is moving this way, it's moving to the right, then the only force that I can count when doing the calculations is this force in the direction of motion. This force in the direction of motion. So when we do our calculations, we need to realize that the force in the direction of motion is all that matters. Again, basic triangle, basic trig triangle problem. I got all tongue-tied there. Basic trig triangle problem. So this horizontal component with this angle theta would be, if this is F, the total force, then this would be F cosine theta, as it always is on the X side of the triangle. Now, you should know kinetic energy and potential energy. You should know what those mean. Kinetic energy means the energy of motion. If an object is moving, it has kinetic energy. Potential energy is the energy stored in an object by virtue of its location. So if I have a rock at the top of a hill, that rock contains potential energy because it could roll down the hill, releasing that energy in the form of kinetic energy. So you should know what kinetic energy and potential energy are. For us, potential energy is not super important, but we do care a lot about kinetic energy. The formula for kinetic energy is 1/2 mv squared. 1/2 mv squared. Again, you don't have to memorize formulas. You'll always have formula sheets wherever you go. But if you'll notice, 1/2 mv squared is mass is kilograms, meters times meters per second will be meters squared over second squared. It ends up being joules. So it's kinetic energy and work are basically the same thing. Let's take a look at a sample problem here. There we go. We have a 3,900 kilogram truck moving at 6 meters a second. What's its kinetic energy? Well, we simply take the formula, 1/2 mv squared right there, plug in the numbers, and you would end up with 70,000 joules. Now, part B wants us to know, what if we double the speed to 12 meters a second? Well, obviously, you could just drop in the 12 meters a second right here where the 6 meters a second is and come up with your answer. But since we've already got this and we know that what I'm basically doing here, let me jump over here, is I'm doing 2 times 6 squared. I can just forget, I know that if this is a 6, I get 70,000. This is a 2, that would get squared. It ends up being 4. And so 4 times 70 is 280,000 joules. However you want to work that one, just realize that there's a little mathematical trick you can play on that one to get you your solution a little bit quicker. Now we're tying it all into one big happy bow. The work energy theorem. As we said just a minute ago, work is in joules, kinetic energy is in joules, and so when you start looking at total work is remember this triangle, this little delta, it means change in is what that delta means. This is a delta. Means change in. It says take the final kinetic energy, that'd be KEF minus KEI. KEF minus KEI. So the total work in a system can be found by taking the final kinetic energy minus the initial kinetic energy. And remember, work can be positive, negative, or zero. So you could end up with a negative answer here. Super important, interesting formula because it ties work and energy together. Now, the question here is, how much work is required for a 70 kilogram sprinter to accelerate from rest? What's the velocity at rest? What does that mean, velocity of rest? So that's going to be the initial velocity. The velocity of rest, as we remember, is 0 meters a second. So that actually makes this problem kind of simple. And it ends up with a VF here, VF of 2.2 meters a second, 2.2 meters a second. So, to solve this problem, we are going to use the work kinetic energy formula. This is our F, this is our I. Plug in the values for F, plug in the values for I. You can do this on your own, just do the math, and you end up with 180 joules. It's exactly the same kind of problem. If I say that the runner's starting out at 1 meter a second and goes up to 2.2 meters a second, the only difference would be I would change this from a 0 to a 1 and everything else, just do the math exactly the same. Obviously this would be lower than, but you get the idea. Here is a problem I want you to take a look at. I'm not going to work this one today. I'm going to work this one for you tomorrow, but I want you to jot the problem down, try and work it on your own, consider it to be your homework for the day, and then we will show you the solution to this one in tomorrow's video. Thank you.